copy that down so that you have up-to-date dates on this. What we're going to be doing today is amine reactions, and then, or amine synthesis, and then amine reactions. And it's a little bit of a strange chapter because as part of the synthesis, we'll actually be learning some of the reactions. So the reactions part is a little shorter, but we'll be covering it in the synthesis. So what we're going to do is kind of divide it up into two broad types of synthesis. If you want to make a primary amine, which would look like this, so R group, we're going to learn 4 different methods to do that you could use. However, if you wanted to have more alkyl groups on the nitrogens to make a secondary or tertiary, the top 4 that I'm going to show you aren't going to help you with that. So the bottom 2, 5 and 6, are kind of more general. They can be used to make primary amines, but they're especially useful for secondary and tertiary. So we'll be learning 6 different syntheses today, one of which is not in the book that I saw. I looked through and through, couldn't see it. That's the Hoffman rearrangement, so that'll be one to good notes. All right, now, this first one, it's actually a review. You've seen part of this reaction in 420, and then we just never did anything with the product. It's an SN2 reaction on an alkyl halide with either N3- or Cn- as the nucleophile. So this reaction itself, just plain old SN2, you're going to take some alkyl halide, and let's pick something like that. The key thing with this, since it is SN2, you can't just pick any alkyl halide. The alkyl halide has to be a decent SN2 substrate. So you can't use a tertiary one, for example. It has to be primary or unhindered secondary. So you can't go too wild with it. So this particular one I have is primary, so it'll work fine. And let's do azide first. So I'm going to treat it with N3-, and we'll use a good SN2 solvent, acetone. And it's just a plain old boring SN2 reaction. And this was the kind of thing that we had you guys predict in Chem 420, only we never did anything further. Turns out, though, you can take that azide and you can reduce it and turn it into an NH2. So it's a way of making a primary amine. As far as reducing it goes, the typical reducing agent that is used is lithium aluminum hydride, followed by, a lot of times you'll see H2O, which is a little bit unusual. In everything we've done thus far, using LAH or NADH4 to do a reduction, we've done H3O+. And that would work here. The problem is, with H3O+, you've introduced an acid. And what is this?
It's a base.
It's a base. So if you use H3O+ to do the workup, which you could do, it's not going to break anything, but if you used it, you would get this guy. It would be propane. And the issue with that is, typically when you do a reaction, you want to extract the product into ether or methylene chloride or something like that, right? But this is a salt. And what are salts? Are they soluble in water or methylene chloride? Water. So if you do an extraction, your product stays in the water layer. So what would you have to do to get it to go into ether? You'd have to deprotonate it. Yeah, so if you use H3O+, to actually get the product, then you'd have to add OH-. That's kind of 2 extra steps. So if you add water, you've added no H+ source, and you get the amine directly. So that's why you'll either see H2O or H3O plus OH minus. They're dealing with that protonation problem. Okay? Another thing your book mentions, and we'll just put it up, there are a number of reducing agents. You could also use a metal and H2 on this. And you would see even other ones. But lithium aluminum hydride is the most common one. Okay? Yeah?
What does the N3 complex look like?
It looks like, it's going to look like that, and it's going to have there and there. Let's see, there's probably a plus and a minus there, I bet. Something like that.
So it's never in like a little triangular ring?
No, it's not. Okay. Let's do it with Cn minus, and you'll see a little bit of a difference. So let's pick an, I don't know, unhindered secondary. We'll do NaCN acetone. And we get Cn right there. And then reduce it. Lithium aluminum hydride H2O. The difference with this is you don't get rid of the carbon. The carbon that I've added as in Cn, the cyanide ion, stays. And so you end up with CH2, NH2. So this came from this. It adds one more carbon, exactly. So if you use N3 minus, you get an NH2 home with that. If you use Cn minus, you get another carbon, an extra carbon and NH2. So really, depending on what you're looking for, you can choose one or the other. Okay, so that's one way of doing it, using a reaction that we kind of already knew. Now, let's look at alkylation of ammonia. This one, when I put it up, it seems almost like the best no-brainer way to do this. So this would be number 2. And this is going to be Rx plus NH3. And the idea is that it would be R and H2. It'd be an SN2 reaction. Looking at that, it seems pretty straightforward. So let's do an example. Since it's an SN2, the conditions apply that we previously seen, primary, unhindered, secondary. And I add NH3. Remember, amines were nucleophiles, and we'd seen them used like that before. So it attacks, kicks out I minus, and I have NH3 plus, and I minus. Now, how do you think I get rid of the positive charge on the nitrogen? I deprotonate, right? What do I deprotonate with?
You always just use I minus.
I could use I minus, but I've got a better base in there. What are amines? They're bases, right? So I've got a ton of a base in there. This guy right here is a nucleophile and a base. And so it can grab that hydrogen for me. And you get NH2. This seems like it should be absolutely great. In reality, it doesn't tend to work so well because, and I think we saw this problem with something else, I forget what, I think Frito-Crafts. This is an electron donating group, right? So I make one of them. And all of a sudden, this nitrogen has a lot of electron density around it. And this whole thing is a better nucleophile. That's a problem. So my product is a better nucleophile than what I started with. It reacts again.
Another one.
And so I get coordinating groups. Guess what happens?
That won't have that.
Yeah, it's better yet. And as you can probably guess, this will go on not forever, to that point. You'll go on to that point. Once that nitrogen has 4 groups, it has a positive charge, and it ceases to become a nucleophile, and it's forced to stop. So this thing is called an ammonium salt, quaternary ammonium salt. And this reaction is really useful if that's what you want to make. You can just put in a whole bunch of alkyl halide and let it go to town, and you'll get your quaternary ammonium salt. However, if what you want is the primary, you're going to end up with mixtures. Okay, so realistically, this gives you mixtures. It's not the best way to go.
I have a question.
Uh-huh.
What's the quaternary ammonium salt used for?
What's it used for? It can be used for, in lab practically, they're used for phase transfer catalysis, which means that they can, they're salt, so they're soluble in water, but they're very organic-y, so they're soluble in organic solvents, and they can actually travel in between the 2 layers and bring ions back and forth with them, and that's called a phase transfer catalyst. So if I need to bring, say, hydroxide, OH minus, from the aqueous layer to an organic layer, I can put in some phase transfer catalyst, and it goes back and forth and brings hydroxide with it. So they do have a usefulness to them. But for what we're going to do, we're not really setting out to make these, so this is a really bad reaction. Probably shouldn't do it. Okay. There is a way, however, to rescue yourself. And that's reaction number 3, the Gabriel synthesis. It's kind of related to this right here. The problem we had was that once I alkylated the amine, the NH3, and made this guy right here, the primary amine, it could react again. And so it went. If I could somehow protect the amine, so it could just add one time, do an SN2 reaction, add one time, and there were, a group was on here, or groups, that I could then take off later, so kind of protect it, I could stop it right here. And that's what the Gabriel synthesis essentially does, is it provides a protected amine group, and so we can just stop it one time. So, you can say it's an alkylation of sort of a protected or a blocked amine. And what they use is something called phthalimid. Phthalimid looks like this. And what we're going to do is we are going to use this nitrogen right here as our nucleophile. As it is right now, it's not a very good nucleophile. The problem we have, it's got a lone pair. So that could go out and attack things. But that lone pair is kind of occupied doing something else. Does anybody see what it is? Yeah, it's got these electron withdrawing groups on it, so it's delocalized here and there. That electron cloud's highly delocalized into the carbonyls. So that lone pair is not useful to us right now. But fortunately, this hydrogen right here is acidic. So what we're going to do in the first step is pull it off, make that nitrogen have a minus charge, and then it's much more nucleophilic. So the way this synthesis works is we take phthalimid, and in the first step, you add OH minus. So it could be NaOH, KOH, something like that. So you add OH minus, and you add one equivalent. When I say one equivalent, what do I mean? 1 mole to 1 mole, right? I don't want any extra OH minus floating around. because then I have a competing nucleophile. So I want it all used up and gone. Then I make the ion. Minus charge. Now this is a pretty good nucleophile. And so what we do is we add an alkyl halide, and I don't know, let's pick some primary but interesting. Benzyl bromide. It's going to be an SN2, so it has to be primary and secondary. And we get this. So I have a CH2 there, bonded to the nitrogen of this phthalate thing. The nitrogen still has a lone pair, but like we just discussed, it's busy doing other things. So it stops right here. This is over with, and we're done. We could isolate this if we wanted to, but it's not what we want. We want to actually cleave right there and right there. Sort of knock that protecting group off of there. And to do it, there are a couple of things you could do. We'll just put both up here. I'll give you both choices. You can do OH minus and H2O in heat. And that gives you your amine. So it cleaves off those groups. They go away as carboxylic acids. And you just get rid of them in the wash. And it leaves that amine attached here. Or another thing you can do is hydrazine. H2N, NH2, and heat. I don't quite know the mechanism of what that's doing, but it gives you the same amine product. That's a much more effective operation because it's controllable. It stops after just one. Okay? So far, no, go ahead.
Is either of those better than the other one, or
No,
just
they're
cheaper,
different.
or?
Just different. They actually came out of two different books. One book we used years ago used OH minus, and the other book we just got out of used hydrazine. And there are even others, but those are the two common ones.
So we can basically substitute that reaction for.
Yes, and it would be a good idea to substitute it for this. This one just gives mixtures. So it's far better if you're going to use an alkyl halide, it's far better to use phthalimid than NH3. So far, I have given you reactions that have, the first three there, have been SN2 reactions. And we had to limit our substrate to things that could do SN2 reactions, right? So primary alkyl halides or unhindered secondary. But let's say that you had a different group, a different alkyl group that wouldn't allow you to do any of those. So as an example, let's say that you wanted to make that. What you cannot do is anything we've talked about so far. Some nitrogen nucleophile. Okay? So number 1's not going to work, number 2 is not going to work, and number 3 is not going to work because it's tertiary. So you need something else. So this is a no. That's where number 4 really comes into play. It's called the Hoffman rearrangement, and it is really useful for making primary amines where the alkyl group is really hindered. So let's do an example. And I'll show you how overall the reaction works, and then we'll go through on how you're going to be building things. And you're not responsible for the mechanism. Sometimes it's in books, and you find it ever, just look at it. It's interesting, but you don't have to do it. So let's go ahead and let's make that one. So you start out with an amide. So to do the Hoffman rearrangement of primary amides, you have to start out with a primary amide. This group right here is an amide. See, double bond O N something. The nitrogen for an amide could have an H2. It could have an R group on it, or even could have two R groups on it. It doesn't matter. The Hoffman rearrangement specifically requires that this be an NH2. So this specifically is a primary amide. So it has to be an NH2 right here. And what you do is you treat it with a halogen, either Cl2 or Br2, and base, and water. And it goes through a mechanism, it's several steps long. But what ends up happening, in a nutshell, is you end up taking the C double bond O out, and it comes out as CO2. So it goes away. And the nitrogen ends up sliding over to take its place. So the nitrogen just skips over. So it is great for R groups that are tertiary or any kind of hindered R group. Or when the R group is a benzene ring is where it's really good too. So you could do, for example, that amide and look at what you create. It was a little more work last time we made that, I think.
I might be missing something, but how do you make that first molecule?
We're going to talk about that right now. Yep. You are missing it right now, you're right. Okay, so is everyone good with kind of the concept? You make an amide, treat it with this set of reagents, the C double bond O pops out, nitrogen slides over. Okay, so the key thing for you, the hard thing, is making the amide. In your book, they kind of presuppose some knowledge. The amines chapter comes after the derivatives chapter, and that's where they teach how to make amides. We haven't gotten there yet. So I'm going to give you guys the reactions to make an amide, but you're not responsible for any mechanism. We'll do tons of mechanism in the next unit for amides. But for now, it's a two-step reaction, just memorize it. So to make an amide, what you are going to do is you are going to start with a carboxylic acid. Everyone knows how to make that. You're going to treat it with SOCl2 and pyridine. And what's that going to do? It's going to put chlorine there, it's going to make an acid chloride. And then you can treat it with NH3. The mechanism is not important, but what you are going to make is that. You make your primary amide plus HCl. So, let's run through our original one right here, how we go about doing that. So, to make that, we decided I had to go through this. guys make that.
Yep.
It's grid yards and blah, 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 the typical stuff. Probably maybe an epoxide would work. You can make that happen somehow. Okay? The key thing everyone messes up is this part right here. It has to be an NH2. So what you cannot do is you cannot decide, oh, I want to have an ethyl group there. And this is such the perfect way to do it. I'll just put an ethyl group right there. You can't. It has to be an NH2. Which means this has to be just an NH2. So it's only for primary amines. It's for hindered primary amines. I even on an answer key once, I wanted an ethyl there, so I put it there. And the students called me out on it. So it's true. Okay. Let's go ahead. And any questions on the first four, which are kind of limited to primary amines? Okay, we're going to branch out now to much more general reactions. Since we just talked about amides, let's go ahead and let's do number 6 first, reduction of amide. What we're going to do in general here, we'll put up some choices, is we are going to take, we'll keep it really generic, R, C double bond O, and H2, that's a primary amide. And we just talked about how you can build those. So you take a primary amide, and you treat it with lithium aluminum hydride, H2O, since we're going to be making an amine. And what that's going to do, in a mechanism you'll learn later, is it turns the carbonyl into a CH2. So it takes this amide unit, this becomes CH2, and it breaks it down into an amine. So if you do a primary amide, you get a primary amine. But your amide doesn't have to be primary in this case. I'm not getting rid of the CO2, or the CO, so I don't need the NH2 to have to be there. I can do this like this. Let's say I put an R group on my hydrogen. So now it's a secondary amide. Hit it with the same reagents. And it would be R, CH2, NHR. It's now a secondary amine. So secondary amide, secondary amine. The nitrogen could have another R group on it as well. It could be fully alkylated. We'll call it R problems. Same thing, reduce it down. The C double bond O turns into a CH2. The nitrogen still has those two alkyl groups on it. Tertiary amide, it gives you a tertiary amine. So it's useful for all three. It just depends how many alkyl groups I have on my nitrogen. So let's do an example. Say on your homework, you're asked to make something like this. Make it secondary. Okay, so say I have to make that guy. And we'll make it through reduction of an amide in this particular case. So what you do, to figure out what is going to be your amide, what it's going to look like, draw it up. So we're going to go backwards to the amide. All right, so that's not really my choice on that side, right? I can't do that. So this is a no. This is what I have to make. I have to make that end. So first choose which half is going to be the C double bond O part. And sometimes the choice is really obvious, like this one. And sometimes you just look at it and you're like, that half's easier to build, so make that half. So I know this is going to come from, going backwards again, it's going to come from the amine and the carboxylic acid, which has been turned into an acid chloride. So far the problem is breaking down pretty easy. This guy will come from the carboxylic acid, which you guys can make that. That's pretty straightforward. How are you going to make the amine that you have to make? You can't just use it on the homework. You have to make it. What are you going to do? Yeah, it's a primary amine, so any one of those up there would work out just fine. So you could do, I don't know, what if you just did this? Br, and you did N3 minus LAH H2O. There it is. Okay? Pick any one of those that is appropriate up there and use it. Okay? Now, the last one. This is kind of the weirdest one. It's got the coolest name though, reductive amination. Very cool name. Okay, reductive amination. This is just kind of odd. It's always like the last one I go to. Just, I don't know why. There's nothing wrong with it, but it just seems weird to me. So this would be, this is 5. The one we just did was 6. Reductive amination. You start with a ketone or an aldehyde. So, keep it real simple. There's our ketone. You make an imine, so you react it with an amine to make an imine. So let's go ahead and let's react it with H2NF, which you would have to make. And we get the imine. And then that imine gets reduced. So it's just a strange, I don't know, it's not as intuitive as the others. So we'll put up a couple of examples so you can see how it works for primary, secondary, tertiary. But first we need to talk about that reducing step. Typically this is all mixed in together. Typically you have the ketone plus the amine plus the reducing agent. That's how it typically is done. It just stirs all up. And then out pops the amine when you're done. So this can present a problem. Right? These ketones get reduced pretty easily. We saw that. So you can, in some cases, and it's possible to isolate if it's primary or a primary or secondary amine. You could isolate this, take it, work it up, clean it up, and then do a second reducing step. It's a lot of work if you don't have to, so no one does that. But what you do is you need a reducing agent to reduce the imine, but not the ketone or the aldehyde. So I need a reducing agent that's selective. Lithium aluminum hydride is a really poor choice because it will hit your ketone or your aldehyde right away. Sodium borohydride, not good. It'll hit your ketone or your aldehyde. What they typically use is they use sort of a weakened version of sodium borohydride. And there are two of them that are common. Here they are. Your book cites one of them. Sodium cyanoborohydride looks like this. NaBH3Cn. Sodium cyanoborohydride. It's not nearly as active as NaBH4, and it will do the imine, but not the ketone or the aldehyde. Problem is it has some toxicity issues, and so there's another one that is a little bit newer that I've seen used in a couple books, and it is this. Again, you can kind of see the borohydride in there with this strange, what's called an acetoxy group on there. This thing is called sodium triacetoxy borohydride. And so you could use one or the other. You mix the whole thing together. So this is or, don't use them together. You mix the whole thing together, let it stir, and it takes care of the reduction in situ, which is a much more efficient way to do it. Okay, so let's do some examples using these guys. We will make primary, secondary, and tertiary amines. All right, to do a primary, I'm going to take a ketone, and I want to make, at the end, I want to make this. So I make it a primary amine. So I want to add just an NH2 right there. That means the nitrogen I'm adding has no R groups. So here, I don't want any R groups on there. So a good choice to make the imine would be NH3. And people use that. Your book gives that as an example. There's another one that's common as well. It's a little easier to handle. NH3 is a gas. And anytime you're trying to use a gas in reagents, it's just, technically, it's just more difficult. So another one that's commonly used, we'll put an or here, is this guy. NH2OH, that's hydroxylamine. The OH ends up coming off during the process. Hydroxylamine is a solid, and so you scoop it out, you weigh it, light is good. It's much easier to use. Okay, neither of these have an R group on the nitrogen, and so you're going through this intermediate, double bond NH. And when you reduce it, it goes to an NH2. Now let's say you wanted a secondary amine. Say I wanted to make, let's see if we can guess the pieces on this one. Say I wanted to make this. To figure out what you need to use, make 1/2 the attacking amine and 1/2 go off my reducing agent here. Add it in. You mix all this together, you get the imine, and when it reduces, you get that. So, let's do another one. What if we had that right there? How would you divide that up? Do you think? So I have to have a ketone, and so my choices really are this, and this, right? That's one choice. Or, the other choice would be this and aldehyde. Okay. Does everyone see how those two would work? Okay, which one would you choose if you were going to build this? I know which one I'd choose. First one or the second?
First one.
First one, that's the choice I would make too. I think I do the first one. That hindrance over there with that tertiary carbon just looks like a bad thing, trying to put nitrogen on that. So I choose the first one. But you do have choices. You know, you can just pick your halves and whichever one's easiest to build. Okay, let's do a tertiary amine now. Let's do something like that. We'll do ketone. A tertiary amine, my nitrogen is going to have 2 R groups on it. So, my product will look like this. When it's all done. So, I just cut it right there. I have cyclohexanone and a secondary amine. Basically what's going on in all these is that for like a tertiary amine, that third R group is coming from the ketone or the aldehyde. So I would mix those two together. And sodium cyanoborohydride. And then you would have to build the secondary amine. On your homework, this is kind of a pain, because you break it apart like this, but you can't just use that, you have to build it. And it's secondary. So to build it, you have to go through either 5 or 6 again, using a primary, and you have to build a primary. So you have to build a primary to get to a secondary, to get to a tertiary. It's a lot of amine building on the homework. But it's repetitive, so. Okay? So that is synthesis. Now, as far as reactions go, we've only got a few. A lot of them we've just talked about. So, let's go ahead and launch into reactions. I'm going to list them all up, and you have to know, but then sometimes we'll just say, just talk about in your notes. So, the first reaction involving amines is you can alkylate them. We just saw that, right? So an example would be like, let's do this. What do you think is going to happen if I treat that amine with excess methyl iodide? What is going to happen? It adds once, right, to make a secondary. The secondary is better. Nucleophile, it adds again, it adds again. The excess here is a key, right there. It's going to put as many on as it possibly can. that, and we saw that unless you want that salt, this is not a good reaction.
Is it going to be carbon groups or is it going to be
What's that?
the ring?
No, it won't be a ring. These are all CH3s. No, there's no way it can form itself into a ring. They're just all CH3s. Okay. Another one is one that we've seen. You can alkylate, you can also acylate. So that's number 2. Acylation, which is where you add that. That's making an amide, is what that's doing. So when you acylate an amine, you are getting an amide. And we already took a look at that. You take an amine, plus a carboxylic, no, it's an acid chloride actually. Carboxylic acid originally. And you end up with acylate. And you've just seen that one. The third one, this isn't really something you tend to want to do. Well, I guess you could. You can oxidize them. You can do oxidation of an amine. They tend to oxidize pretty readily. And what you end up doing, let's just do an example of oxidation of an amine. You could make, let's say you made amylin, and you treated it with an oxidizing agent like CR3H2SO4, for example. This is usually one of those things where you're doing a synthesis and you have an amine somewhere and you're trying to oxidize an alcohol, and this is a whoops or an oh, what am I going to do with that amine kind of reaction. What it's going to turn into is it's going to turn into an NO2. So amines tend to get oxidized and start adding oxygens. They have a couple different forms. You can have, and I'll just give the forms, less oxidized and more oxidized, and you can see the different things you might see. The first thing the nitrogen can do is it could, if it's secondary, primary or secondary, you'll get this. So I'm just going to fill one right there. Is it could add an OH. That's a hydroxylamine. You oxidize that further, you could end up with forming a double bond up. That's called a nitroso. And if you oxidize that even further, that's where you get NO2s. So it just keeps adding oxygens, starting to form as many double bond oxygens as it can. Typically in this, if you have an amine like on a shelf in the stockroom, and we're going to run into this even in our next experiment, we're going to use a lot of amines. And you'll open the bottle, and some of them will be really dark brown, and some may even have sludge in the bottom, where they start to decompose. What often happens is when you open up an amine, like when we did these reactions a couple of years ago, you have this nice, pretty, clear liquid. We use it, we cap it, we put it under the hood until like next August, and it starts to oxidize from oxygen. And what happens to your amine is it forms, depending on how bad it is, various stages of this. And it turns into kind of black gunk. And you guys are going to see some black gunk in the next experiment. These won't be as pretty as kind of the things you're used to. So to protect them, a lot of amines are stored as salts. So to prevent it, you can do this. If that can oxidize, so you protect them as a salt. And so amines are often sold as salts, which are shelf stable. Okay.
Was there ever a way to kick off an NO2 group from benzene?
No, no, there isn't. Okay, so oxidation's kind of a whoops reaction. Okay. This next one, it's interesting. I've never quite been able to figure out why you'd want to do it, but it's interesting. And the most interesting thing is really the trivia and the name. This is called the Hoffman elimination. So what number are we on? Hoffman was very busy. He had rearrangements, he had eliminations, very busy guy. So Hoffman elimination. To give you some background, let's just scribble over here. If I have an OH, and I want to turn it into a double bond, what am I first going to have to do? I protonate it, right? H2SO4 and heat, we learned that. Okay, good. What was the function of the H plus in H2SO4? Protonate it, okay. And why? Why was that important?
Makes it into a
Because
leading
it
group.
turns it into a good leading group. Okay. So if I can turn the OH into a good leaving group, like protonate it, or turn it into a Cl or a Br, then I can use base and get rid of it. I gotta turn it into something in order to get rid of it. The Hoffman elimination uses this exact same idea, only from the standpoint of a nitrogen. So what we're gonna do is we are gonna take this nitrogen and we're gonna do an elimination and get a double bond. So we have to turn it into a good leaving group. What we're going to do is we're going to turn it into a salt, put a plus on it, by putting CH3s all around it. So we're going to alkylate the daylights out of it. So what they do is they do CH3I XX. And I've got C and C and C and a plus. This is now a good leaving group. It looks really similar to that protonated OH. It's got a plus charge. If I kicked it off, it would be trimethylamine, pretty stable. It's a great leaving group. And so now I just treat it with a base. And the base they use, it's a strange base. They use silver oxide and water. I don't know if you remember in Chem 400, I think it is. They, at least they used to, take oxides and mix them in water and you test their pH and stuff.
Yeah.
They're basic. They make OH minus, right? A small amount of OH minus. So what happens when you mix it with silver oxide and water, the counter ion originally is I minus. The counter ion becomes, let's redraw this guy, C, becomes OH minus. So you're essentially giving the reaction source of hydroxide. And then it's heated, so let's put some heat in there. What happens is an E2 reaction. I've got base, I've got a good leaving group, but check that out. Here's the trivia part. When we had a choice of where the double bond could go, we named those two possibilities. One was Zaitsev, and the other was what? Hoffman product. Guess where that came from? This reaction right here. You get the less substituted alkene. Isn't that interesting? So that's where that name, Hoffman product, came from, is the Hoffman elimination. Yes?
Can this only be done with primary heat?
No, it could be used on other ones too. And we can do an example in just a minute. Okay, so why is it happening? Well, when we wanted to make a Hoffman product before this, alkyl halide, and let's just draw one up. BR. How would I put the double bond right there? Yeah, that guy. What was the key thing about the base?
It's gonna get in.
Couldn't get in. Why not?
Because it's
Giant, right? It's a very hindered base. This is the same idea, only my base isn't hindered, my substrate is. This is a giant group. And so OH minus can get in easily at the very, very far away part of it. It's going to be much more difficult to try to squeeze in here past it. So it's much easier to grab the less hindered hydrogen. So it's the same principle. Hindrance is driving it, only it's not the hindered base this time, it's the hindered substrate. Now, Naisha asked if it has to be an NH2 all the time, and it doesn't. You can do them, let's do one like this. All right, let's do that. See, I want to do a Hoffman elimination on that guy. We do CH3IXS. And I have C plus. And now I've got to figure out where reaction's going to occur. So I put the H2O heat, and let's see if I want to.
probably carbon dioxide.
Yeah, none of these are that pretty. Let's put this. Let's go like this. Let's adjust our molecule. Yeah, go put that there. I like this one better. It's a better example. Otherwise, it was too much the same. Okay. These, you have to go identify where the hydrogens are that could be eliminated first. So, I am going to be forming a double bond and breaking something like that. Break this off or break it off there. So, this is my leading group right here. So I could remove this hydrogen, form a double bond, kick that out. I could remove this hydrogen, form a double bond, kick that out. I could remove this hydrogen, form a double bond, kick it out. Or this one. There's a lot of choices. Which one is the least hindered of them all? This one right on the CH3.
Yep.
So OH minus will grab this one, forms the double bond, kicks that leading group out, and I'm going to have this. Here's my double bond. Here's my ring. The nitrogen is still attached, but it left the carbon it was attached to. When it's in a ring, the nitrogen ends up dangling off one side of the ring.
Could put more excess in it and get it.
I could put excess into it again, yeah, and just kick it out completely.
Oh, but it stops right there.
It stops right there, unless I go on and add I'd have to do the whole reaction again. But it stops right there, that nitrogen is kind of dangling. So I'm not sure, it's an interesting reaction. I'm not sure why you want to do it though, because usually to get the NH2, you start with an alkyl halide. And so I would just use a bulky base and call it good, but whatever. So I guess if you had to eliminate an amine, there it is. Okay. Now for my favorite reaction just about in OChem. I love this reaction. It's easy. So, acid is HNO2. That's what nitrous acid looks like. And when you treat something with HNO2, say you have a primary amine, and you treat it with HNO2, you make that species right there. It forms an N2 plus, and I'm not going to ask you guys the mechanism of that. This right here is called a diazonium salt. So if you have a primary amine, it will go to a diazonium salt. The bad thing about this is it decomposes. And it falls apart to give you nothing useful. So you can make it, but it's not like you can do anything with it. But turns out if your primary amine is on a slightly different R group, like a benzene, so if you have aniline and you treat it with nitrous acid, you get a diazonium salt. And this is somewhat stable. You wouldn't probably put it in the fridge until next Monday and come back and hope things are okay. It's not stable like that. But it's stable enough that if you keep it cold, you can use it to do things with. This one, when it's just an alkyl group, plain alkyl group, falls apart, you can't use it for anything. But this guy will stick around long enough you can add things to it. And so what we're going to see today is we are going to add all sorts of different types of nucleophiles. And learn how to make different benzene derivatives that we couldn't really do before. So it has a really big utility in substituting benzene. So let's go ahead, and there are a couple things we have to talk about, a couple specifics, before we actually do anything with this. The first, nitrous acid itself isn't something you buy in a bottle. You actually generate it in situ. So what you guys are going to see in the book is you'll see aniline and going through the diazonium salt. And you're going to see NaNO2 and HCl. Sometimes H2SO4. So an acid. So NaNO2 and HCl will give you nitrous acid. So you don't actually ever put droppers of nitrous acid in there. You never add drops. So we'll take sodium nitrite and HCl. And you're going to do this reaction after spring break. And that you'll be adding those two things to your test tube, keeping everything cold. Okay? As far as how that works, so you have nitrous acid, which I'm going to do like that. The actual reactant is this ion right here. That's the actual reactant, is NO+, which is the nitrosonium ion. And that's what's actually doing the reaction, is that nitrosonium ion. So let's take a look at how in the world that's happening. got it written out somewhere here, here we go. HON, double bond O. Okay, write nitrous acid just like that. We're generating it in the presence of acid, HCl. So the first thing that happens is we propane. Water's a good leaving group. It comes off, and you are left with nitrogen and a plus with a double bond O, the nitrosonium ion. Why would that form? Why would water come off and leave you with this weird looking thing?
Didn't you say endo so
It's got to be stabilized somehow.
stable, yeah.
I mean, not that stable, but somewhat. How's it being stabilized?
The water purifies.
Yeah, it can be stabilized by resonance from that. So it's not totally unreasonable that it might form. Okay, so let's go ahead and show you what can be done with that diazonium salt that you're making. So you make N2 plus. And let's take a look at what you can add to it. And let's do a table here. Reagent. Let's have an idea that we'll do this. Reagent going to X. The things you can put on there. Here's the reagent, here's what X would be. You can put on, using CuVr and HBr, guess what that's going to put on? A bromine, good. You can put on a CuCl, HCl. What's that going to put on? Chlorine. NaI. Come on, NaI, what's it going to put on? Okay, I. All right. Here's one that we haven't seen. CuCN, KCN. It's going to put a CN on there.
That's nice.
H3O plus, what do you think that would put on? An OH. Good. Remember I said there's a better way to do this than fuming sulfuric acid and then NaOH at 300 degrees? This is the way. Okay, it's much, much better if it's cold. And then the last one, this is weird, and next time we'll see why you want to do it. Hypophosphorus acid, H3PO2. It puts on an H.
Oh,
It makes the N2 plus completely go away. And now, just to give you an idea of why this is so important, and then I'll stop and hand your test out.
no.
It allows you to do something you couldn't do before, sort of torture you before. Let's say I wanted to make, do a simple one. Say I wanted to make this, ClEr. Can I? Right, what's the problem?
They both direct ortho-para.
They're both orthopara directors, right? How do I get NH2? Remember, this comes from an NH2, right? What is one step before the NH2? Do you remember?
NO2.
An NO2. What kind of director is an NO2?
It's a meta director.
Director. So what you do is it allows you to use the two different directing effects. One of the NO2, use it to go meta, change it to an NH2, use it to go wherever you need to go, and then change that group to whatever you want. So what we're going to do is we are going to take benzene, HNO3H2SO4, put an NO2 on there. Now I'm going to change this eventually to a chlorine, but not right now. So it's a meta director. Let's brominate. ER2. FDBr2, FDBr3. Okay. Now how do I change NO2 to NH2? Yeah, just LAH or something. Now it's an NH2, and I've got a Br there. I make the diazonium salt, NaNO2HCl. Now I can turn that diazonium salt into lots of things. I want to turn it into a chlorine, so CuCl and HCl. Ta-da, there it is.
You're so cool.
Isn't that cool? Next time we'll do a couple of examples. In one, we're going to use the directing effects to do what we want, and then I'm going to make the group go away because I don't need it anymore. Okay, it's going to be a directing effect slave, and then we're just going to kick it off. Yes?
The test he wants to do
On the test, I don't really care. You can use HNO2 if you want to, as long as you're aware that you have to actually make it. I don't know in the standardized test which one they're going to do. So you need to be comfortable with both. Alrighty, here we go.